Good day, I am Hannah Chrisselle Leynes and I'm a second year EE student. And today I'm gonna talk about the design and demonstration of a JFET amplifier, especially the N-channel JFET amplifier. First of all, what is an FET amplifier? A field effect transistor, or also called as FET, is a three-terminal semiconductor device. Its operation is based on a controlled input voltage. By appearance, JFET and bipolar transistors are very similar. However, BJT is a current control device, and JFET is controlled by an input voltage. So the function of a junction field effect transistor depends upon the flow of majority carriers, electrons or holes only. So basically, JFET consists of an N-type or P-type silicon bar containing PN junctions at the sides. And following are some important points to remember about FET. First is the gate. So by using diffusion or alloying technique, both sides of N-type bar are heavily doped to create PN junction. These doped regions are called gate. For the source, it is the entry point for majority carriers through which they enter into the semiconductor bar. Next is drain. It is the exit point for majority carriers through which they leave the semiconductor bar. And the last one is the channel. So it is the area of N-type material through which majority carriers pass from the source to the drain. So there are two types of JFET. So one is the N-channel JFET and P-channel JFET, but we will focus on the N-channel JFET. So next is the basic demonstration on basic N-channel JFET circuit showing the common characteristic curves. So today we're gonna do the figure 1 simulation. So you're gonna need components, two voltages, V1 and V2. Then we're gonna add the NJF, or also called the N-channel JFET. And we'll connect the components. Then we'll add the ground. And for our voltages, we will label V1 as VGS and set it to negative 3 volts, negative 3 volts. And for our N-channel JFET, we will take the model 2N3819 with the manufacturer Vishay. And for our V2, we will label it as VDD and set it to 20 volts. So as shown in the circuit was set up to produce the common source characteristic curve. So we will perform a DC sweep with the command .dc VDD 0.20 0.02 VGS negative 3 0.5. So the voltage drain was swept from 0 to 20 volts for values of gate source voltage over negative 3V to 0V in 0.5 volt steps. So we will run the circuit and getting the current for VDD. As you can see, simulating the plot of drain source voltage or VGS of 0 volts, and successive curves have an increment of 0.5 volts. In the graph, at the reverse bias voltage, no drain current will flow, and it is called the pinch-off voltage. So, using the formula delta VDS over delta ID, we will be given a result of output resistance of FET. For figure 2, for a self-biased JFET amplifier, we will now add 3 resistors. The gate resistor holds the JFET gate potential at 0 volts and sets the input resistance. The source resistor is used to bias the source terminal. To set the voltage gain, a drain resistor is used. On the right is the DC load line. The load line starts on the x-axis at the maximum supply voltage and is a straight line to the Q point to the y-axis. The DC load line is where the circuit will always operate. Now that the load line is complete, we can calculate the resistor values. So the resistance is determined by the x-intercept divided by the point where the load line crosses the y-axis. Zooming in, the value is about at 11.9 milliamperes. Calculating the total resistance, so we have RT equals 20 volts over 11.9 milliamperes, so we will have 1,680 ohms. And then from the circuit, the Q point crosses the line at VGS at -1 volts and source current of 5.324 milliamperes. To bias the gate to the necessary voltage, a source resistor is added. As VGS is equals to negative ID times RS. Rearranging the equation and substitute values of -1 volt over negative 5.324 milliamperes, we will have 188 ohms. Then calculating the difference of RT and RS, so 1,680 minus 188, the remaining 1,492 ohms will be used as the drain resistor, as seen in the circuit. So the parameters of a JFET amplifier, so we have the AC drain resistance, or also called RD, transconductance, which is the GFS, and application factor, which is the U. So for the AC drain resistance, it is the ratio of change in the drain source voltage, delta VDS, to the change in the drain current, which is the delta ID, at constant gate source voltage. So it can be expressed as RD equals delta VDS over delta ID at constant VGS. For the transconductance, it is the ratio of change in drain current, delta ID, to the change in gate source voltage, delta VGS, at constant drain source voltage. So it can be expressed as GFS equals delta ID over delta VGS at constant VDS. For the amplification factor, it is the ratio of change in drain source voltage, delta VDS, to the change in gate source voltage, delta VGS, at constant drain current, delta ID. So it can be expressed as U equals delta VDS over delta VGS at constant ID. So there are some important advantages of a junction field effect transistor, and there are also some important disadvantages. So first is the advantages. So the junction field effect transistor, or JFET, is a majority charge carrier device, hence resulting to less noise. It has high input impedance, low power consumption device, can be fabricated in a small size area. And it occupies less space in circuits due to its smaller size and has negative temperature coefficient of resistance. So they possess higher temperature stability. For the disadvantages, the main disadvantage of the junction field effect transistor, or JFET, is the relatively low gain bandwidth product. The performance of JFET goes down as frequency increases due to feedback by the internal capacitance. Thank you for listening.